let me start from where we stopped. So we had this amplitude, which is a set, which is a collection of correlators of the trace of t. It involves 4 insertions of t, 3 and 2, and they are organized in such a way that it has interpretation of the scattering amplitude for a background dilaton. I was discussing before, in this external dilaton, it's purely a trick to find the right combination of correlators that has the interesting properties, okay? It's in no way a physical field, it's just a trick. On the other hand, you know that correlators in quantum field theory, if you go back to the original source method of Schwinger, can be interpreted in terms of scattering amplitude for external sources. So in the end, it's the same old story. And we were able to argue that this amplitude, which is a collection of correlators, is finite, meaning that when we go from the theory in flat space to the theory coupled, so normally when we have a theory and we have renormalized it, so in other words, we have organized in such a way that all things that we compute are finite and well-defined. Okay, if we take this theory and couple it to something else, there may arise new divergences, okay? And we have to take care of them and normalize the new couplings, okay? So when you couple the dilaton with this background, which lives in this background metric to your quantum field theory, you generally have additional divergences. On the other hand, I argued using simple power counting that if you consider dilatons, external dilatons that satisfy the on-shell condition box omega equals 0, so that they can really be interpreted as external quanta with p square equals 0, okay, really in the sense of scattering amplitude of massless quanta. But if another condition had been necessary, I would have chosen another condition, but it happens to be this one the right condition. Then in this situation, all possible counter terms, all possible divergences disappear or vanish apart from a cosmological constant. So the amplitude is completely defined by the theory in flat space plus a constant term. And the part which is calculable, I argued, is just controlled by the A coefficient in the anomaly in the conformal limit. And in the non-conformal limit, it's going to be something more complicated, but it is calculable and finite. And then using this argument, I simply use a dispersive, using these results, we established a dispersive argument that relates the value of A in the IR, this is the integral along this line of this amplitude, the value of A in the UV, and they are related by an integral from the IR to the UV of a positive quantity. This positivity just follows from unitarity, okay? It's just the positivity of the scalar product in Hilbert space, and this positivity is associated with the positivity of what we could interpret as the cross section, okay, of the cut. So we have like, we can interpret this as 2 dilaton going into the QFT and scatter back. And the forward, the imaginary part of the forward scattering amplitude is the cut of this diagram, and the cut of this diagram, the imaginary part of this is just the optical theorem, is equal to this diagram. So 2 dilatons that go to any state of the QFT squared. Okay, so this quantity up to kinematical factors is just the cross section for absorption, the thing I write here. And notice that the units are not totally okay, because this is dimensionless, and this is energy, and this is cross section would be. But it's just simply because I took the coupling constant of the dilaton equal to 1. I didn't dimensionally, I didn't give it dimension, okay, in this computation, but if you give it dimensionality, then there would be a constant everywhere, but it's not important. So if you forget this, so this is the cross-section times some dimension full quantity. The crucial thing is that it is positive, okay? And again, this cross-section is purely an artificial object, okay? The crucial thing is positivity. Now, there are several comments here. This integral IRG, which is the integral, so there is, what the hell is this? So I integrate over this. And this IRG is the integral along these two lines, okay? The integral along these two lines gives me the difference in the A coefficient between the UV and the IR. So if in the UV and the IR you have ordinary generic conformal field theories, this quantity will be finite, okay? So this integral must be finite. It's just the difference between two parameters of our theory. The theories are normalized, so there's no infinities. It's nice you can directly check in this integral, okay, in the integral here. And you can do it as an exercise, okay, that IRG is equal to the integral of the imaginary part of the amplitude over s squared ds. And sorry, s cube. And the amplitude, as you remember in the asymptotics, whether UV IR goes in the UV and the IR, in the UV goes like AUV, S square, 1 plus corrections from relevant operators. So they go like powers of M over S. And normally these have imaginary power, because normally you have non-integer powers, and this is going to have imaginary parts. And similarly in the IR, you have AIR S square 1 plus S over M to a power. This if you have relevant or irrelevant. So you have relevant deformation in the UV and irrelevant in the IR. And it's interesting that you can check that this scaling, as soon as this power is positive and this is positive, will be such that this integral is convergent in the IR and the UV. The case where you have logarithm behavior, like in QCD, it's slightly more tricky, so check. And you see precisely that basically you have that the notion of convergence to the fixed point coincides with the notion of convergence of this integral, okay? Notice that the convergence of this integral happens under broader conditions than what you would, for those who have heard about the Froissart bound. Froissart bound is telling you that the imaginary part of the amplitude goes less, like cannot be, well, okay, in some situations, more than S log S. Here you can allow the amplitude to go almost like S square, simply because this is not genuinely a physical process like the ones you have in QCD. But forget the last comments. Those who know about the Froissart bound may consider the comparison for the convergence of this integral to what they know about the Froissart bound, and they see that they are not related. That's all I want to say. Those who have never heard Froissart bound, forget about what I said. So you can check that the convergence of this integral has to do is in one-to-one correspondence with the convergence to a fixed point of the flow. In other words, just transfer this here. You will see that this integral here. Okay. Let me do it again. In the UV and the IR, using this formula here, I will have that the integral will be ds. There's an s square here. There's an s cube there. Becomes over s, and then you have a UV 1 plus something convergent, something like a power m over s. Sorry, the imaginary part is not coming here. This is only the imaginary part. This does not contribute to the imaginary part. So the imaginary part is only the integral of ds over s. There's an s square here eaten by that. And then you have, if the flow is convergent, this should be, and if the flow is determined by relevant operators, in the UV, you will have some positive power of mass here. So here you have m over s to some positive power, and that is convergent. It's enough that this positive power is epsilon to make it convergent. And the very definition that the operator is relevant is coincides with the fact that this coefficient is, the exponent is positive. So you see that there's a connection between convergence of this integral at large S and the relevance of the deformation that is controlling the flow away from the UV fixed point. And the same argument works in the IR, in the other way around. The convergence at S going to 0 works fine. ds over S, S over M to some positive power, if at the IR fixed point we are flowing only controlled by irrelevant operator, which is again the assumption that in the IR we only have irrelevant deformation of the fixed point, and so we flow into a new fixed point. Okay, with respect to the IR fixed point, we only have irrelevant deformation, and again, this guarantees convergence in the IR. Of course, it had to be so. It had to be so. Everything had to be finite because, as we argued, okay, the amplitude up to cosmological constant is automatically normalized once you normalize your original theory. There are no new divergences. So there cannot be any logarithmic divergences, okay? There cannot be any, very often you can read the divergences in quantum field theory by doing dispersive integral. If you have a logarithmic divergence, you can interpret that as the need to add some counter term. Here we see that we don't need anything. And this matches very nicely the analysis we had done previously, which was saying that the only divergence in the amplitude was a constant, real cosmological constant. Okay, and in particular, therefore, the second derivative of the amplitude in the UV and IR, or wherever you want, is controlled by something that we can compute. Okay, in particular A. So the finiteness has to do with the analysis we did before. Now, it turns out, and this is what I will do in the next half hour, that I will use the fact that in general, regardless of the assumption that the theory is flowing to a CFT, I will just use the finiteness of this integral to constrain the asymptotic itself. Basically, I now use the argument the other way around. I will use the fact that this integral has to be finite to prove that the theory must flow to a fixed point with conformal invariance. This is what I will do in a moment. Now, just a few comments, okay? Just 2 comments before going to the new problem. So what does the A theorem imply? It implies that when you have a flow from a UV CFT to an IR CFT, A here is bigger than here. So you now may ask yourself a completely crazy question. Is it possible that now I deform the theory in such a way that this is not attractive, but I can add a slight relevant, I can change slightly my parameters in the UV such that the theory flows toward this fixed point, but it doesn't really reach it. That there is a relevant operator turned on here that makes me go away, makes me go back. It will be a quantum field theory that you look at it at different scales, and at a certain point it will look back the way it was before. It's as if you go from quarks and gluons to pions. Then pions interact, they have some strong dynamics, and at longer distances, you can describe the theory in terms of quarks and gluons. Okay? You may think this is crazy. Okay? Well, okay. Not so crazy. Okay? By the way, gauge quantum numbers, as you say, they're not in the case of color, you don't see color charges. So that's, first of all, it's already okay. There are no colored states. So you can go from pions in principle. You may say, well, there are no fermions. That's probably more, but you can have non-trivial things. I don't know. This case is not good. Perhaps if you had a theory where there were only scalars in the UV and then bound states, who knows? But anyway, in quite general, this cannot happen. Okay. Notice, on the other hand, that there are examples in non-relativistic theories where the cyclic behavior appears, and this happens. I'm not an expert of it, but let me tell you when it happens. It happens when you have, in non-relativistic physics, when you have a situation where you have two non-relativistic heavy objects, like two nucleons, okay, like a neutron and a neutron. And the scattering length, say in the S wave, is going to infinity. Okay, this is very similar to what happens when you have the deuteron. Okay, and you have a very tiny, when it goes to infinity on one end, it's imaginary. I mean, where the potential is attractive, but the scattering length goes to infinity. So you have bound states that are very, very large. Okay, they're arbitrarily large. In the limit where the scattering length goes to infinity, the bound state is huge. This is almost what happens in the deuteron. The deuteron is much bigger than the typical scale of nuclear physics, which is 1/n². Okay, it is way bigger, precisely because there is such an accident. Okay, it's not a big fine tuning. It's like a cancellation of 1 in 5, 1 in 10, perhaps 20. Okay, let's say 1 in 10, depending on whom you talk to, and whether you look at the cancellation in the energy or the momentum, So in this situation, there is Efimov showed long ago that when you send the scattering length to infinity, you have in the three-body problem, in the three nucleon interaction, you have a recurrence of bound states, which form a sort of a geometric series with binding energy that go up to 0. And this set of states can be understood in terms of an energy flow in the non-relativistic trilinear coupling theory, where the coupling flows periodically. Okay, this is known as MF. It has been reinterpreted, I think, by Wilson. Okay, and this structure is known as Efimov cycle. Okay. Now something like that cannot happen in relativistic theory, apparently, or there is indication that at least when at intermediate stages you have a CFT, approximate CFT, this cannot happen. Maybe it can happen if the theory is never even close to a CFT. It just goes around and is not even close to a CFT. Not even going through a CFT as it seems to be doing here. So this is interesting. I should say that I don't know yet of any insightful applications in particle physics. For instance, a possible application would have been the following. So we know that A decreases. Okay, so we know what. You may ask yourself, okay, what I'm telling you now, it's a failure, so don't expect much. Okay, I'm telling you, let's see what you can do with this. And so in principle, you can try to see whether the A theorem is telling you something about the occurrence of a conformal window in QCD. Let me tell you the story. Okay, so QCD with NF flavors. Okay, n equals 0 QCD. Without supersymmetry, as a beta function at the one loop beta function, which is proportional to 11/3 number of color minus 2/3 the number of flavors. Okay, and for a very large number of flavors, the theory is when I change the number of flavors. Here it's 11/3 and color. So when the number of flavors is bigger than 11/3, 2/3 number of flavor is bigger than 11/3 number of colors, the theory is IR free. So the sign of the beta function is negative, so the coupling. Sorry, it's the other way around. Okay, standard beta function is positive, so the theory, so the coupling grows in the UV and decreases in the IR. In the far IR, if there are no masses, the coupling goes to 0. So the theory is free, is what you call trivial, assuming the quarks are massless. It's similar to 5⁴. Okay, so this is IR free. At sufficiently low number of flavors, we know, like in QCD, for instance, number of n color equal 3, number of flavor equal 3 or 4. We know that the theory confines with chiral symmetry breaking. Okay, so confinement here at a certain point, there is confinement with chiral symmetry breaking. Okay, And the IR theory here is made what? If n flavor, you have an SUN flavor close SUN flavor group broken down very much like in QCD to SUN. There are theorems that tell you that this is what happens. This is papers by Waffa and Witten of the 80s about the pattern of symmetry breaking in QCD-like theories. So you know this is the pattern of breaking. SUN cross SUN is broken to SUN. And you have, this gives rise to NF square minus 1 Goldstone bosons. Okay? So you start from a theory which in the UV has massless quarks and gluons, and you get down to a theory which has a definite number of Goldstone bosons. And then there is a region in the between where I can put a question mark. Although we have an idea of what happens, there is a window here, and the question is where the window is. It's certainly starting here. Well, let me tell you another thing. There is a certain place here, if the number of color is big enough, where you have conformal field theory. If the number of colors is sufficiently large, we know that here there is a conformal, the theory goes in the IR to conformal fixed points. This is Banks-Zaks. The so-called Banks-Zaks fixed points. We don't know how big this window is from where the theory goes to a conformal fixed point, but indication, in supersymmetric gauge theories, when equal 1, we know for certain where it is. This is the results obtained by Seiberg in the 90s. So we know there is a significant window where this happens. And presumably there is also a window without supersymmetry. And recent lattice explorations are giving some indication that is the case. The question is where is this window? Okay, where is the cross from confinement to CFT behavior in the IR? So if there is CFT behavior in the IR, okay, there's an interacting CFT in the IR. So you may ask yourself whether the A theorem gives any insight on this, and the answer is no. Okay, but let me at least show it to you. So and let me tell you why. Okay. So it could have, but it doesn't. So you could, under the assumption that you have confinement with chiral symmetry breaking, you know how many degrees of freedom you have in the IR, and you know that the theory in the IR is free. It's a set of free Goldstone bosons. So you can compute A in the IR in this case. So one may wonder whether when NF becomes larger, since this guy grows, okay, perhaps you can no longer saturate AUV minus AIR. But that is not the case. And that is not the case because what really matters, or what dominates A in the UV, is the number of vectors. One vector has a value 62. Okay, it's like a gold coin. Okay, and scalar have value 1. Okay, and that's it. Okay, and then then you can check, and even from the point of view of A, even if the chiral symmetry breaking confining phase were going up to here, the IIR less than IUV will be satisfied. So it's not giving you, unfortunately, any insight on that, although it could have. So many people have had this thought independently, but it didn't. This is just to give you what you could do with this thing, but this cannot be done. Okay? Perhaps there are other insights. Perhaps you guys can think of other ways of understanding in a general way where this window is. Perhaps there is more than just the A theorem to understand the properties of flows. Okay? Perhaps this is just we're scratching the surface of a bigger set of relations. Who knows? So let me stop with this and let me go to the next subject. Okay, and I'll try to discuss it very quickly. Okay. So I now want to see. I now want to use the finiteness under broad condition of this dilaton scattering amplitude if you want, of the quantum effective action for the dilaton on shell. I show that it is finite, and from this finiteness you can deduce interesting things, and you can deduce interesting things under these assumptions. Okay, so let me tell you what is my assumption. Consider a situation, and the assumption I'm making here, I'm making it for technical reason. If I make these assumptions, which captures a class of interesting theories, okay, then the step you have to take to get some interesting result is totally trivial, okay. So in the end, is the triviality follows from the assumption, but the assumption is covering a sufficiently broad set of cases to make it interesting, okay. So let me tell you what is the assumption. I want to study the properties of a renormalization group flow in the neighborhood of a fixed point, okay, and in the neighborhood of a fixed point that is conformal invariant, okay. So let me tell you what. So I have a theory, okay, that's a CFT, could be free, could be interacting. I don't need to make any assumption regardless whether it's free or not, okay. The only thing I know is that it's a CFT. And the other thing I want to know is that this theory has, I assume that this theory has some marginal parameters, okay. It has scalar operators of dimension near 4, okay, that allow a very slow flow, okay. An example of that are free theories with dimensionless couplings, okay, like ordinary weakly coupled 4-dimensional gauge theories with weak gauge, Yukawa, and quartic scalar couplings, okay. But you can imagine more general things where you have a strongly interacting CFT that has its own marginal deformations or quasi-marginal deformation. And I want to turn them on, okay? I want to turn them on. The question is, what happens to the flow in the neighborhood of this fixed point? Can the flow in this neighborhood do this? And remaining is the neighborhood doing some cycle, okay? Can the flow in this neighborhood do some crazy things like here, ergodicity, and never go anywhere and remaining there forever, okay? So I'm trying to understand whether asymptotically any of these crazy behaviors can appear in this neighborhood. I know, or for instance, it starts from this CFT fixed point and it goes to an SFT fixed point in the same neighborhood, okay? So there's a theory which is first conformal and goes to a scale invariant theory just by RG flow. What do I know of by direct computation of examples of these guys? All the examples I know are that I start with a CFT and I end up to a CFT. These are in supersymmetry. These are Banks-Zaks. And okay, there are also examples from ADS-CFT, but that's very much related to supersymmetry, okay? So all the examples we know, what the theory does, it either goes back to itself or it goes to another CFT. So the asymptotic behavior in the far UV, it's always a CFT, okay? Now, for what we know, okay, for what we see in the explicit example, the question is there a general rule? And now, in order to see whether there's a general rule, whether I can prove that this is the only possibility, I make the assumption, okay, that the flow is always in a neighborhood of this fixed point. It doesn't go in a regime where I cannot view the theory as a small perturbation of this point. Notice, for instance, in Banks-Zaks, I go from a CFT to a very weakly interacting CFT. There are two different CFTs, but they're very nearby in coupling space because that's a weak, very weak deformation of the other one, okay? I've turned on very small couplings. They're two distinct theory, but there's an expansion parameter, a small parameter that controls the difference of all things, all observables in the two theories, okay? So I work on the assumption that there is this small parameter, okay, that I can work with. And the small parameter is simply the beta function, okay? So I'm assuming that in all these regions that I'm going around, the beta function is always small and all couplings evolve slowly. There's no region where the running becomes large. Okay? So in particular, when you run to a totally new fixed point, you run slowly, and then when you start getting close to it, you start going fast, and then eventually you slow down, but there is a region where you go fast. It's the region where the theory changes completely. Like when you go from the theory of quarks to the theory of pions, when you get near 1 GeV, the gauge coupling of QCD runs like crazy. Okay, I will not be able to describe things like that. Okay, my result will rely on the use of perturbation theory, but of course, yeah, I mean, it would be interesting to be able to say more. But already, as concerned what I'm going to say now, the situation was not clear until 2-3 years ago, and there were even claims that cycles existed in the neighborhood of free field theories. Okay, so the basic idea is to use that the amplitude is finite up to cosmological constant terms. So more precisely, all the UV divergences that I would encounter in the computation of this correlator are taken care of by renormalizing the theory itself in the absence of an external metric. Okay, so when I write this amplitude, okay, they only need I can write it as a finite amplitude as a function of the running renormalized coupling of the original theory. Okay, this is to say the couplings that control these deformations. And in the CFT limit, this amplitude, the forward amplitude, the coefficient of the forward amplitude, as I've shown before, is simply the A coefficient. From now on, I'm neglecting the cosmological constant because, as I showed you, it never really matters. So in this situation, I can do exactly a variant of the computation I did before, but I don't even consider taking a small and large. I just take two arbitrary circles, okay, half circles, and I integrate around this contour. The integral around these circles, okay, if you look at my expression here, okay, so let me say the integral around the circle here, okay, is the integral of ds over s cubed of A of s. Okay, using this equation, this is simply the integral of ds over s of alpha of s. And around this circle, ds over s is di theta. Okay, and I multiply by I. Okay, I get rid of the I. So it's the integral in d theta of alpha of s. Okay, this integral here. So this integral here, so s, so where s is equal to some real s, e to the I theta. Okay, sorry, I didn't say it properly. Okay, so this integral here, I call it alpha bar of the absolute value of s. Okay, and you can prove easily that this thing is real just by using the properties of the amplitude, okay, crossing, reality, the properties I showed this morning in the transparency. Okay, so this quantity is real. This quantity is real, and when the theory is conformal, it coincides with the A coefficient up to a fact, it's minus 4A. Okay, coincides with A up to a coefficient and a sign. So now I can consider this integral, okay, and I have the integral on this, on that, and gives me precisely this difference. And then I have the integral on the line, on the segment. There's just the integral of the imaginary part of the amplitude times the d log of s. Okay, so it's the integral or in d log of a positive quantity, because by unitarity the imaginary part of the amplitude is positive. Okay, so I have that the difference between these two, between the value of this quantity, which is a finite quantity at two different energy scales, it's an integral, okay, of a positive function. Now, if I assume that, let's say that we go towards the IR, okay, and if I assume that the theory keep flowing in the neighborhood of this point forever, okay? Whether it goes to new fixed points, whether it goes to an SFT, whether it cycles around some point in the near neighborhood, whether it goes around in a crazy way but in the neighborhood. In all these circumstances, forever, okay? I can imagine taking this S1 to 0, okay? And I know that these quantities are finite because they're just function of the coupling in this region. They're just finite couplings, okay? They are power series in finite coupling, okay? So they can be written perturbatively in terms of these couplings. In other words, but they're finite. They're function of finite couplings. They don't involve any new divergences, so they're finite, okay? In particular, so if there was if the theory were flowing to a new, any divergence that would appear in this integral here, okay, when I send this 1 to 0, would have to be interpreted as the theory flowing to a new fixed point, and there are the new theory has logarithmic ultraviolet divergences, okay, because the log will be seen from the IR theory in terms of a log of the UV parameter, okay. This is perhaps not totally clear. If you find this not totally clear, just go back to what I said before. It's a finite function, okay? So the finiteness of this function implies that asymptotically this imaginary part has to behave in such a way that this integral is finite. So this is the integral of a d log, okay? So in order for this to be finite, let's focus on the IR, but you can do exactly the same in the UV, okay? Assuming that in the UV the theory flows to a quantum field theory. In the UV, of course, the theory could go to, I don't know, to a non-field theory. But let's imagine the UV keeps being defined by a quantum field theory. So that would also have to be finite when I send this to infinity. So the net result is that since this integral here is the difference of two finite quantity, it must be convergent both in the UV and the IR. So that means that the asymptotic behavior both in the UV and the IR of this imaginary part is 0. Okay? So, and that's simply following from the absence of any counter term that could allow me an interpretation of a divergence. And now, what it turns out now is that the vanishing of this imaginary part allows you to make a direct conclusion on the properties of the property of the flow. So, for instance, consider, and here I will only discuss this quick thing. I will not. I don't want to spend time and get into a discussion that makes all the details more clear, but let me do it very quickly. So what do we have? What is this amplitude? So the amplitude consists of three classes of things, 4 T's, 3 T's, and 2 T's, plus the cross terms. The imaginary part amounts to taking the cut of each of these, okay? And the cut of each of these, okay, is as an interpretation of the absorption of the two dilatons into any state of the QFT. So this is just the probability of absorption of two dilatons into the QFT, and one can easily convince that if you look at the combinatorics, that this square is the sum of these squares, is the sum of squares that involve either two insertions or one insertion. Okay, there are all the possibilities. Okay, if you want the imaginary part of this guy here with the right coefficient, with the right combinatorics, plus it's equal to squared. And when you put them together, this with itself gives the first term, this with this gives you this, and this with this gives you that, with the right coefficient, okay? So this is a perfect square because it's a cross section, okay, just the optical theorem, and the form is given by this. So it's a transition. This is very similar when you do deep inelastic scatter. I mean, any QCD process where you take some field coupled to a QCD operator, and perhaps you have a transition. Well, normally here you would have a proton. Here we have vacuum, because the initial state has no state of the original. You could view this. This is the analog of studying E plus E minus or photon into hadrons, okay? It's very similar. You would have here the electromagnetic current, the QCD vacuum, and here a QCD, all possible QCD states, okay? Here you have not just one current insertion, but also two current insertions, okay? Because rather than just a photon, we have two dilatons going in. The two dilatons can go in at the same point, and then it looks like one current insertion in QCD, like the photon, okay, the off-shell photon created previously by E plus E minus. Imagine, okay, let me give you an example. In QCD, I have E plus E minus, and then I have a photon, and then here I have QCD states. Back to this. The imaginary part of this, of E plus E minus to E plus E minus, is E plus E minus into any hadrons. But in fact, the E plus E minus are not really important. This is like some virtual photon going into QCD, decaying into QCD, and back to itself. The imaginary part of this is proportion to the cross-section, total cross-section for a virtual photon into QCD. Okay? And this is very similar. Okay? And you have terms with one insertion of T and two insertion of T. Now here is the important thing. When you have a situation close, when you, under the assumption that we are close to a conformal fixed point, the beta functions are small, okay? In other words, we are sitting near a fixed point, a conformal fixed point, so T is a small operator, okay? T is made up of proportion to a sum of operators with small coefficients, okay? And therefore, there's a notion that this guy is more important than that, because there are two powers of T. So in particular, this first guy here is proportional to the sum of the beta function times all the operators associated with the deformation. That's just standard result in QFT. While here you have higher orders, okay? You don't have just beta square. It's more subtle than that. You have beta d beta. You have beta times anomalous dimension. So it's not beta square, but it's somewhere in the between beta square and beta. And it needs to be explained better, and I will not do it, okay? Qualification needed. This goes outside the boundary of today's lecture, but the details can be worked out. So at leading order, under the assumption that the flow is near a fixed point, you can neglect the quadratic term, and the imaginary part is dominated by this. By the very assumption of perturbativity, this cannot undo the effects of that, okay? Otherwise, you would be non-perturbative. So if you assume that you are sitting near a conformal fixed point, means that you can treat the deformation perturbatively, you can neglect this in the eye of that. And at the end, the fact that you are using only the two-point function of T is what makes a connection with the two-dimensional proof that the only flows have CFT endpoints. Basically, with the assumption of perturbativity, I've thrown away all the peculiarity of four dimensions. And the proof becomes very much the same as in two dimensions. So what I need is for this quantity to flow to zero in the asymptotics, okay? Now this quantity here is if the operator is a physical operator, by unitarity, this quantity here, which is dimensionless, is positive and non-zero. This quantity here can either be zero or positive. If it is zero, it just means the operator, it's a fake. Your operator is zero, okay? Your operator has no effect. It's simply used an operator which is a combination, which is proportional to the equations of motion. But any physical operator will give you a non-zero result, okay? So this metric here is strictly positive definite. So then the imaginary part is just a strictly positive metric times the beta function computed at the value of the running couplings. So in order for this integral to be convergent, the beta function has to asymptotically go to zero. So the theory asymptotically must be conformal. So all these other possibilities are ruled out. Okay, and there was a little bit of controversy with some results found by Ben Greenstein and collaborators, and this controversy was eventually solved, and we agree that the cycles they seemingly had found in a neighborhood of a free field theory do not correspond to physical cycles, but they correspond to cycles that are unphysical and that can be undone by a Fielder definition. So there's no real cycle in their theory. the genuine beta goes to 0, and the trace of T mu goes to 0. So the theory is conformal. So that's quite non-trivial. The fact that this happens, given as you regard it from, as you view it from their computation, means that the structure of the beta functions or the flows of this of quantum field is very non-trivial. For this result to happen, you must have some really clever relation between beta functions of different couplings at different orders, because the couplings, the fixed point that we're finding was under the assumption of Banks-Sachs, so where you assume that the first order beta function is 0 because of an accident, and then you have a reshuffling of different orders in the beta functions. There's a one loop beta which is accidental of the order of a two loop beta. So you have some non-trivial interplay between different orders, and everything works out in such a way that at the end the theory flows to a conformal fixed point, and it was not guaranteed at the onset. And the reason why he was perhaps guaranteed at the onset is because of these arguments, and these arguments are absolutely non-trivial because they're making a wide use of all the properties of the theory, in particular of the structure of counter terms, the absence of counter terms and for on-shell dilatons, and dispersion relation and unitarity. So unitarity is very much important in all this, while when you do the perturbative computations, you don't fully see it, okay? Although you know that the signs, and not the coefficient, but the signs of beta, perhaps also the coefficient when you compare different orders, the signs of the beta functions are very much related to unitarity. The very fact that QED, the coupling flows large at short distances, is a clean consequence of unitarity. The fact that in the spectral decomposition of two current correlators, fermions, you only have positive weights, okay? The only reason why you get opposite signs in non-abelian theories is that you have intermediate states that are not physical, okay, and that have not positive norm, okay. Like I said, when you have charged gluon fields. So unitarity is very much important in describing RG flows, as we already knew. So I'm basically done with all I had to say. Perhaps I wish just to conclude with one little thing concerning non-perturbative, a non-perturbative proof. Okay. So now let me just switch. I'm almost done. Yeah, 10 minutes fits well. So we know that we know lots of things now. Okay, at least within the assumption that the flow sits near a conformal fixed point. We know that the standard model is extrapolated to a new theory above the weak scale, different than the standard model. And if there is a separation of scale, the theory is approximately scale invariant. And if the theory, it could be, I mean, if the theory is approximately conformal invariant, then we can definitely say that in the neighborhood of this flow, nothing else than the approach to another conformal fixed point can happen. The standard model cannot cycle around forever around some other point. We cannot guarantee yet that the standard model may flow to a completely crazy scale invariant theory without conformal invariance, which is in no way in the neighborhood of a conformal theory. Let's say an SFT, a scale invariant theory, which is not approximately close to a conformal theory. That we cannot yet rule out, or we cannot rule out the standard model does cycles that are so huge that are never close to a scale invariant theory. That, no way. In fact, I wonder if we will ever be able to rule that out. Because when you have a theory which is not doing some big cycles, it's not even approximately scale invariant anywhere. So you don't even know how to do power counting. At least I would not be able. It doesn't make it. There's no approximate dimensional analysis. The theory does not have any approximate scale invariance. That could be interesting, actually, for the hierarchy problem. There's no selection rule for dimensions. Maybe that's what the doctor ordered. I don't know. I cannot rule that out or in, or I cannot I don't have any tools. I don't have any tools to get this bull by the horns and whatever, by the tail even. Now, on the other hand, if you assume there's something more that you can say under the assumption that the standard model flows to a non-trivial scale invariant theory, even one which is not directly related to, not close to a CFT, but far away, but scale invariant. And that is because when you're scale invariant, you have scale invariance. So you can do dimensional analysis. You can say, oh, this will go like a constant because it is dimensionless. There's dimensions. Okay? You can say, oh, this is dimension this. Okay, it is dilatation symmetry. So in particular, in this situation, you can say that the imaginary part of the amplitude, which in our definition is dimensionless, if it is non-zero, it must be a constant, okay? Because there are no scales that you can put in. It cannot have any S dependence, okay? The theory has no scales. This is dimensionless. The only thing you can write down is a constant, okay? Any dependence on the energy would require dimensionful parameter, okay? The amplitude is dimensionless, okay? So if the theory is scale invariant and not conformal invariant, the imaginary part of the amplitude is not zero, but just a constant. Remember, at a conformal fixed point, the amplitude is real, is simply given by the A anomaly times S square at the fixed point. So the imaginary part is zero, okay? On the other hand, if the theory is only scale invariant, all you can say is that the imaginary part is a constant. And now what happens if the imaginary part of A is a constant? Well, if the imaginary part of A is a constant, then this integral is totally infinite. Okay, this integral here the imaginary part of A, if this is a constant, this is the integral of ds over S times this constant, and this integral is infinite, is divergent both in the IR and the UV. Okay, so so again, if we know that the amplitude has to be finite, and here, if you want, there is a caveat which I will say in a moment. If we know that the amplitude has to be finite, then the only possibility for this constant is zero. Okay, and if the constant is zero, then it means that this constant is just the amplitude, the full amplitude for two dilatons being absorbed in the QFT squared. Okay, is the probability of absorption. Now, as I told you before, the probability of absorption consists of two terms. There's an insertion of T and two insertion of T. At weak coupling, you can neglect this compared to that, and we derived the conclusion that if this is zero, T has to be zero. But if the theory is not weakly coupled, it's not a weak deformation of CFT, there's no reason to treat this as small compared to that. And what could happen is a particularly malicious cancellation between these two terms. Okay, such that T is a non-trivial operator, but C is zero. Okay, so this is what must happen in a scale invariant field theory where the amplitude does not have any pathology. So what pathology could have the amplitude? And this is something that we have been thinking about it only recently. And in fact, my collaborator, Marcus Luthi, I think is mostly thinking about it while I'm doing other things. Okay, maybe he has already a paper coming out. I don't know. There is the option that this thing is infrared divergent. Okay, and if the forward amplitude has some infrared divergence because at t equals 0 there is some pole, it's like a Pomeroy pole or something like that, then the whole story has to be rearranged. It would mean that this class of theory is a class of theory where this dilaton amplitude is in a totally different class, is divergent, infradivergent, and so It's not UV divergent, but infrared divergent. And I don't know. I would have to think about that. I'm just mentioning things that are not baked. Perhaps I shouldn't. But there is this thing to think about. If that is not the case, then this is what you need. And you need this C to be 0, and this implies a non-trivial vanishing theorem for the energy momentum tensor. It means that the matrix element of the Fourier transform of T, okay, when the P1 and P2 are on shell, must be 0, okay? And this is very interesting, okay, because you see, it's interesting because you see, it means that this is an insertion where two dilaton come at different points, generically, while there is the point where two dilaton come at the same point. So this only has S wave. This is a scalar. So this has only S wave, L equals 0, while this has all possible waves, 0, 1, 2. So the vanishing of this amplitude tells you that, of course, there must be a clever compensation in the S wave between the quadratic and the linear term, which is not trivial. Okay, it means just T square and is equal to minus T in the S wave. And in the higher than S wave, the matrix element of T are 0. Okay, this seems like a very crazy constraint. And now, starting from this constraint, there have been additional papers in the last 2 years, one by Komargowski and collaborators, one by Yonekura, and perhaps more, because I'm not checking the web that constantly, who claim that this allows you to prove in general, by generalizing and going to the next step, then T is 0 as an operator, and that the theory must be conformal. I honestly don't fully understand these proofs. Okay, I cannot say that they're wrong, but just that I don't fully understand them. They're probably too complicated for me. If you understand them, please explain them to me. Okay, but so this is an open problem. Okay, in my opinion, this is still an open problem. I think also the authors would agree that these proofs are sort of physicist proof. They're not yet under full mathematical rigor. Okay, and I think that the problem of the infrared divergence I mentioned before is also shedding some ghostly light on all these things. Again, I think this is an open problem. I think it's very interesting. It's an interesting question in 4-dimensional quantum field theories. Could be that the standard model is extrapolating the UV to a scale invariant theory, not conformal. Okay, you say, come on. Standard model is extrapolated to the standard model, there's nothing else, okay? Could be, okay? But if you start thinking as crazy things like the ones Strumi is thinking, I think this is less crazy. So somewhere in the between, no, I'm all for crazy things. Okay, this was not criticism. Okay, the question is whether they're crazy enough. That's the only question. Okay, now just to show you that we are not completely crazy, it's essential in all this argument that you have unitarity. Okay, so we argued that if the amplitude is finite, okay, if the amplitude is IR finite, given that there are no if the amplitude is finite, then by this dispersion relation, this integral must be finite. Therefore, the coefficient C must be 0. It's a self-consistent thing. But the coefficient C in a unitary theory is a sum of positive terms. Okay, in a unitary theory is a sum of positive terms. If I didn't have a unitary theory, it would still be a sum of things, but they could be some positive and some negative. If the norm of the states is not all positive, I could imagine a situation where I have sum of negative and positive things, and at the end I get 0. Okay, I know I must get 0, and if the theory is unitary, given that all the terms are positive, I know that each and every term is 0. But it would be interesting to check what happens in a non-unitary theory. So non-unitary conformal field theories are known. Okay, they're known, and these non-unitary conformal field theories are not structures that are completely crappy from the point of view of physics. They don't have an interpretation in terms of ordinary particle physics theories, but they have interpretation in terms of statistical mechanics system. In particular, in 4 dimensions, they have interpretation of statistical mechanics systems in 4 space dimensions. Okay, 4 space, 5 dimensions with time. Okay, so this system exists. Okay, and there exists a system of this type that corresponds to scale invariant and non-conformal invariant theory. One example pointed out long ago by Coleman and Jakiv and studied more recently by Riva and Cardi in 2 dimensions is the theory of elasticity. You can consider the theory of elasticity in 4 dimensions. It's a theory that describes, if you interpret it as a statistical mechanics system, the leading equilibrium behavior of a solid, okay, of a deformations of a solid. And the main degree of freedom is a vector, a mu, without gauge invariance. So it's a vector without gauge invariance, so the theory is not unitary, okay? It cannot be interpreted as a unitary theory, but it's a perfect interpretation in terms of a theory in Euclidean space, where these are positive, okay? And it is scale invariant because there is no scale, but it's not conformal invariant. And there's even a beautiful candidate for the virial current. It is this. This is the virial current. Okay, this current V cannot be written as the derivative of something, and the trace of T mu mu is the divergence of this. So that is an SFT. And now you can apply all our machinery to this theory to see whether we were totally dumb or not. In particular, you can compute the absorption of a dilaton by this theory, okay, according to our rules, okay? You have the 2 insertion and the single insertion. And now you have to be careful because if you interpret in terms of particle physics, not all final states have positive norm, and you have to sum them with the right sign, okay? And to do that, you just do loops, okay? Loops will take care of it with the right sign, okay? Simply some of these photons have residues that have g mu nu, and the g mu nu has 3 pluses and 1 minus, and that's already taking care of these negative norm states. So you just do the computation, and you find that the partial cross-section, okay, so the absorption of 2 dilatons going to these photons in any arbitrary direction is non-zero, okay? But if you sum over all final states in all directions, of course some polarization contribute negatively, but if you sum over all of them, you find that the total cross-section is 0. Okay, it's a non-unitary theory, precisely as it should, okay? And the way it works is, in this case, because you have the theory is non-unitary and there are cancellations between different states. So all that we say about the fact that C has to be 0 is correct. So we did not make mistakes there. Okay, we're not missing anything. The amplitude is infrared finite. It's a well-to-do amplitude. And the way all the things are realized very cleverly is by the fact that there are cancellations. So the basic point is that T is a very non-trivial operator, but the particular matrix element of T, where you sum over final states, are 0. So T is non-trivial, but its inclusive matrix elements are 0. So that's the way it works. I don't know. Okay, so this is my story. Okay, I think I'm done.